What if everything we've been taught about the beginning of the universe is wrong? What if the grand narrative of cosmic genesis, the one we've embraced with such certainty, is merely a reflection of our current limitations rather than an absolute truth? Consider for a moment the possibility that the universe didn't burst into existence from a singular point of infinite density. Imagine that the story we tell ourselves about creation is incomplete, a partial glimpse through a clouded lens at something far more complex and mysterious than we've dared to conceive. We live in an age where the Big Bang Theory stands as an almost sacred pillar of scientific understanding. It's taught in classrooms, presented in documentaries, and accepted as the definitive account of how everything came to be. 13.8 billion years ago, we're told, all of space, time, matter, and energy erupted from an infinitesimally small point in an explosion of cosmic proportions. The universe expanded, cooled, formed atoms, ignited stars, and eventually created the conditions for planets, life, and consciousness to emerge. It's an elegant narrative, one that seems to explain so much about the cosmos we observe today. But what if this story, despite its elegance and explanatory power, isn't the complete picture? What if the universe harbors secrets about its origins that challenge this foundational narrative? The question isn't whether the Big Bang Theory has been useful or whether it's explained countless observations. The question is whether it represents the ultimate truth about cosmic origins or whether it's a stepping stone toward a deeper understanding we haven't yet grasped. To truly appreciate the possibility that the universe might not have begun with the Big Bang, we need to understand what the theory actually claims and why it gained such widespread acceptance in the first place. The Big Bang isn't just a speculative idea someone dreamed up one afternoon, it's a conclusion drawn from decades of careful observation and mathematical reasoning. In the early 20th century, astronomers made a startling discovery. Edwin Hubble, peering through powerful telescopes, noticed that distant galaxies were moving away from us. More remarkably, the farther away a galaxy was, the faster it appeared to be receding. This observation suggested something profound. The universe itself was expanding. If the universe is expanding now, physicists reasoned, then it must have been smaller in the past. Wind the clock back far enough and you arrive at a moment when everything was compressed into an incredibly hot, dense state. This was the birth of the Big Bang Theory, the idea that the universe began as a cosmic fireball and has been expanding and cooling ever since. Additional evidence strengthened this picture. The cosmic microwave background radiation, a faint glow of light permeating all of space, was discovered in the 1960s. This radiation appeared to be the afterglow of the universe's hot, dense early state, precisely what the Big Bang Theory predicted. The abundance of light elements like hydrogen and helium in the universe also matched theoretical calculations of what should have formed in the intense heat of the early universe. For most scientists, this evidence seemed conclusive. The Big Bang became the standard model of cosmology, the framework within which all other cosmic phenomena were understood. Textbooks were written, careers were built, and entire research programs were dedicated to refining the details of this cosmic origin story. Yet, even as the Big Bang Theory achieved dominance, cracks began to appear in its foundation. These weren't minor inconsistencies that could be easily explained away. They were fundamental problems that struck at the heart of what the theory claimed about the universe's beginning. One of the most troubling issues is known as the horizon problem. According to the Big Bang model, different regions of the universe that are very far apart should never have been in contact with each other. They're separated by distances so vast that light hasn't had enough time since the Big Bang to travel between them. If these regions were never in contact, how could they possibly have the same temperature? Yet, when we observe the cosmic microwave background, we find that it has an almost perfectly uniform temperature across the entire sky, varying by only tiny fractions of a degree. This uniformity suggests that somehow, impossibly, these distant regions managed to reach thermal equilibrium despite never having been in causal contact. The standard Big Bang theory struggles to explain this uniformity. Physicists have proposed various solutions, most notably the theory of cosmic inflation, which suggests that the universe underwent an incredibly rapid expansion in its earliest moments, stretching tiny regions that were once in contact to cosmic scales. Inflation helps solve the horizon problem, but it also raises new questions. What caused inflation? What mechanism triggered it? And what made it stop? These questions remain largely unanswered, and inflation itself requires fine-tuning of physical parameters that some find unsatisfying. Then there's the flatness problem. The geometry of the universe appears to be remarkably close to flat, meaning that parallel lines would remain parallel forever, rather than eventually converging or diverging. For the universe to be this flat today, it would have had to be extraordinarily, almost impossibly flat in its earliest moments. The slightest deviation from perfect flatness in the early universe would have been amplified over billions of years, resulting in a universe that looked dramatically different from what we observe. The fact that our universe is so close to flat seems to require an extraordinary coincidence in the initial conditions, unless something in the universe's history acted to flatten it. Even more perplexing is what's called the singularity problem. If we follow the Big Bang theory to its logical conclusion, tracing the universe backward in time, we arrive at a moment when all of space was compressed into a single point of infinite density and infinite temperature. This is what physicists call a singularity, a place where the laws of physics, as we understand them, break down completely. At a singularity, our equations produce infinities and cease to make meaningful predictions. General relativity, Einstein's brilliant theory of gravity and spacetime, predicts that such a singularity must have existed at the universe's beginning. But this prediction is also a confession of ignorance. When your theory tells you that the laws of physics break down, it's essentially admitting that it can't describe what actually happened. Many physicists are deeply uncomfortable with singularities. They view them not as real features of the universe, but as signposts indicating where our current theories reach their limits. If the universe truly began at a singularity, then we're forced to accept that the moment of creation lies forever beyond the reach of scientific understanding. But what if the singularity isn't real? What if it's an artifact of applying general relativity to a situation where it no longer applies? Quantum mechanics, the physics of the very small, might have something crucial to say about the universe's earliest moments, something that could eliminate the singularity altogether. This brings us to one of the most fundamental tensions in modern physics, the incompatibility between general relativity and quantum mechanics. General relativity describes gravity and the large-scale structure of spacetime with remarkable accuracy. Quantum mechanics describes the behavior of particles and forces at microscopic scales with equal precision. Both theories have been tested extensively and have passed every experimental challenge thrown at them. Yet, when physicists try to combine these two pillars of modern physics into a single unified theory, they encounter seemingly insurmountable mathematical difficulties. At the moment of the Big Bang, according to the Standard Model, the entire universe was compressed to a size where quantum effects should have been dominant. This means that any complete description of the universe's origin must somehow merge general relativity with quantum mechanics. We need a theory of quantum gravity, a framework that can describe the behavior of spacetime itself at the smallest scales. Despite decades of effort by some of the brightest minds in physics, we still don't have a fully developed, experimentally verified theory of quantum gravity. Without such a theory, our understanding of the universe's first moments remains fundamentally incomplete. Several candidates for a theory of quantum gravity have been proposed, each offering different insights into what might have happened at the universe's beginning. String theory, perhaps the most famous of these attempts, suggests that the fundamental constituents of reality aren't point-like particles, but tiny vibrating strings of energy. In string theory, the universe might have more than the three spatial dimensions we experience. There could be additional dimensions curled up so small that we can't directly observe them. Some versions of string theory suggest scenarios where the Big Bang wasn't really a beginning, but a transition from a pre-existing state. Loop quantum gravity, another approach to quantum gravity, focuses on the structure of space-time itself, treating it as woven from discrete loops rather than being smooth and continuous. In this framework, the singularity at the Big Bang might be replaced by a quantum bounce. The universe, instead of emerging from nothing, might have contracted from a previous phase, reached a minimum size determined by quantum effects, and then rebounded into the expansion we observe today. This would mean the Big Bang wasn't truly the beginning, but rather a transformative event in an eternal cosmic cycle. The possibility of a bouncing universe has deep philosophical implications. If the universe underwent a bounce rather than beginning at a singularity, then time might extend infinitely into the past. The Big Bang would be reinterpreted not as the moment when time itself began, but as a dramatic transition between different phases of cosmic evolution. This idea isn't entirely new. Throughout history, various cultures have embraced cyclical cosmologies, imagining the universe as eternally oscillating between creation and destruction. Modern physics might be rediscovering these ancient intuitions in a new mathematical language. But the bounce scenario faces its own challenges. For the universe to contract and then bounce back, there must be some mechanism that prevents complete collapse into a singularity. Quantum gravity effects might provide this mechanism by creating a kind of quantum pressure that pushes back against gravitational collapse. However, working out the details of how this would happen requires a complete theory of quantum gravity, which we don't yet have. We can write down equations that suggest a bounce is possible, but we can't be certain these equations accurately describe reality until we can test them against observations. This highlights a crucial challenge facing all alternatives to the Big Bang theory. They must not only be mathematically consistent, but also make predictions that can be tested through observation. A theory that explains everything but predicts nothing testable isn't science, it's speculation. The strength of the Big Bang theory has always been its ability to make concrete predictions that could be verified. The cosmic microwave background, the abundance of light elements, the relationship between distance and recession, velocity of galaxies, these were all predictions that turned out to be correct. Any alternative theory must be able to explain these same observations while also addressing the problems that plague the standard Big Bang model. Some alternative cosmologies propose that the universe is far older than 13.8 billion years, perhaps infinitely old. In these models, the structures we observe today might have formed gradually over vastly longer timescales than the Big Bang allows. The galaxies, stars, and planets didn't all descend from a single explosive event, but accumulated over eons through different processes. These ideas challenge not just our understanding of the universe's beginning, but also our understanding of how cosmic structures form and evolve. One such alternative is the steady-state theory, which was actually a major competitor to the Big Bang in the mid-20th century. The steady-state model proposed that the universe has always existed in roughly the same condition, with new matter continuously being created to fill the voids left by cosmic expansion. This ensured that the average density of the universe remained constant over time, avoiding the need for a dramatic beginning. For a while, steady-state theory had serious supporters among prominent physicists. It offered an elegant solution to the philosophical discomfort some felt about the idea of a cosmic beginning. However, the discovery of the cosmic microwave background radiation in 1965 dealt a severe blow to steady-state theory. This uniform background radiation was exactly what the Big Bang theory predicted, but seemed difficult to reconcile with a universe that had always existed in the same state. Most physicists abandoned steady-state theory in favor of the Big Bang, though a few continued to explore modified versions that might accommodate the new observations. The cosmic microwave background became the smoking gun evidence for the Big Bang, the observation that seemed to settle the debate once and for all. Yet, even this evidence isn't quite as definitive as it might seem. The cosmic microwave background tells us that the universe was once in a hot, dense state, but it doesn't necessarily tell us that this hot, dense state was the absolute beginning. It's possible that something came before, some earlier phase that left the universe in the condition from which the Big Bang expansion proceeded. The radiation we observe might be the afterglow, not of creation itself, but of a transformative event in a universe that already existed. This possibility opens up fascinating scenarios. Perhaps our universe is just one in an infinite series of universes, each emerging from the collapse of its predecessor. The Big Bang we observe would then be the white hole emergence from a black hole in a previous universe. Or maybe our universe is embedded in a higher dimensional space, and the Big Bang represents the collision of higher dimensional membranes, like cosmic sheets colliding and generating our three-dimensional universe as a byproduct. These ideas sound like science fiction, but they emerge from serious attempts to extend our physical theories into realms we can't yet directly observe. The concept of a multiverse takes these ideas even further. If our universe is just one among countless others, each with potentially different physical laws and constants, then the Big Bang might simply mark the beginning of our particular cosmic bubble within a much vaster reality. In eternal inflation models, the process that drove the rapid expansion of our early universe never truly ends. Instead, it continues indefinitely in other regions of space, constantly spawning new universes with different properties. Our Big Bang would be just one of infinitely many, each separated from the others by distances so vast that communication or interaction between them would be impossible. The multiverse idea raises profound questions about what we can ever hope to know about reality. If other universes are fundamentally unobservable from our own, can we meaningfully say they exist? Science traditionally deals with claims that can be tested through observation and experiment. If a hypothesis makes no testable predictions, many philosophers of science would argue it falls outside the domain of scientific inquiry. Yet some physicists contend that the multiverse is a natural consequence of theories we already have good reasons to believe, and that dismissing it simply because we can't directly observe other universes would be premature. These debates touch on deep questions about the nature of scientific explanation itself. What makes a theory scientific? Is it enough for a theory to be mathematically beautiful and to solve problems with existing theories, or must it also make unique predictions that can be tested? Different physicists have different views on these questions, and the lack of consensus reflects genuine uncertainty about how to do science when dealing with cosmic origins and the universe's earliest moments. Meanwhile, observational cosmology continues to advance, providing new data that might help discriminate between different models. Increasingly precise measurements of the cosmic microwave background have revealed subtle patterns in its temperature fluctuations. These patterns contain information about the conditions in the early universe, including the nature of whatever process, whether conventional Big Bang expansion or something more exotic, produced them. Every new space telescope, every improved detector brings us closer to being able to test specific predictions of alternative cosmological models. Gravitational wave astronomy, a field that only recently became possible with the detection of ripples in spacetime from colliding black holes, offers another window into the universe's history. Primordial gravitational waves, if they exist, would have been generated by quantum fluctuations in the earliest moments of the universe. Detecting these waves could provide direct information about what happened in the first fraction of a second after the Big Bang, potentially revealing whether inflation occurred, whether there was a bounce, or whether something even stranger took place. Dark matter and dark energy, two mysterious components that apparently make up 95% of the universe's total mass-energy content, also factor into questions about cosmic origins. We don't yet know what dark matter and dark energy actually are, despite strong evidence for their existence from their gravitational effects. Understanding their nature might shed light on the universe's early history. Some alternative cosmologies propose that dark energy isn't a property of empty space, but rather evidence of modifications to gravity that become important at cosmic scales. If gravity works differently than Einstein's theory suggests, this could have profound implications for what happened at the universe's beginning. The very concept of a beginning might itself be problematic. Our intuitions about time are shaped by our everyday experiences, where events have clear before and after relationships and time flows in one direction. But quantum mechanics has shown us that at fundamental levels, reality doesn't always conform to our intuitions. Time itself might be an emergent property, something that arises from more fundamental processes rather than being built into the fabric of reality. If time is emergent, then asking what happened before the Big Bang might be like asking what's north of the North Pole, a question that seems meaningful but is actually based on a misunderstanding of the underlying geometry. Some theories propose that time doesn't exist in the way we think it does. In certain formulations of quantum gravity, the fundamental laws of physics are timeless, describing relationships between physical quantities without any reference to time's passage. Time emerges only when we look at the universe at larger scales, as an approximate concept that works well in our everyday world but breaks down at the universe's smallest scales and earliest moments. If this is correct, the question of what caused the Big Bang or what came before, it might be fundamentally misguided. These ideas push us to the limits of human understanding. We're trying to comprehend events that took place under conditions so extreme that nothing in our experience can adequately prepare us for them. The universe at the moment of the Big Bang was hotter, denser, and more energetic than anything we can create in our laboratories or observe in the cosmos today. The physical processes occurring then were governed by laws we're still struggling to fully understand. Yet, despite these challenges, the human drive to understand our origins persists. We want to know where we came from, not just as biological beings, but as parts of a cosmic story that stretches back to the beginning of everything. This drive has led to remarkable achievements. In just over a century, we've gone from believing the universe was static and eternal to understanding that it's expanding and evolving. We've measured its age, mapped its large-scale structure, and identified the key events in its history. We've discovered that the atoms in our bodies were forged in the hearts of stars that lived and died billions of years ago. We've learned that the simple hydrogen atoms created in the Big Bang underwent countless transformations to become the complex molecules that make up living organisms. This is a story of breathtaking scope and grandeur, one that places humanity within a cosmic context that our ancestors could scarcely have imagined. Yet, for all we've learned, fundamental mysteries remain. The Big Bang Theory, despite its successes, leaves crucial questions unanswered. Why did the Big Bang happen? What determined the specific properties of our universe, like the strength of gravity or the mass of the electron? Why is there something rather than nothing? These are the kinds of questions that keep cosmologists awake at night, questions that might require new physics or even new ways of thinking about reality itself to answer. The possibility that the universe didn't begin with the Big Bang opens up new avenues for addressing these mysteries. If the universe emerged from a pre-existing state, perhaps through a quantum bounce or a collision of higher dimensional objects, then we can potentially trace causality back further than the Big Bang allows. The properties of our universe might be explained by the properties of whatever came before, shifting the ultimate question of origins to an earlier phase of reality. This doesn't necessarily solve the problem. We can always ask what came before that earlier phase, but it might make the problem more tractable by allowing us to study a continuous chain of cause and effect rather than confronting an absolute beginning where causality breaks down. Alternative cosmologies also offer different perspectives on the fine-tuning problem, the observation that many physical constants appear to be precisely calibrated to allow for the existence of complex structures and life. Change certain constants by even a small amount, and stars wouldn't form, atoms wouldn't be stable, or chemistry as we know it wouldn't be possible. In the standard Big Bang framework, this fine-tuning seems to require either extraordinary luck or some explanation for why the constants have the values they do. The multiverse offers one such explanation. If countless universes exist with different constants, it's not surprising that we find ourselves in one where conditions allow for our existence. But alternatives to the multiverse explanation exist. If the universe underwent cycles of expansion and contraction, physical constants might evolve from one cycle to the next, gradually settling into values that produce stable, long-lived universes. Or perhaps the constants aren't truly constant at all, but vary across space or time in ways we haven't yet detected. Some theories suggest that what we call fundamental constants might actually be dynamic fields that took on their current values through processes occurring in the universe's early history. If this is correct, then fine-tuning isn't a cosmic coincidence, but the outcome of physical processes we can potentially understand and study. The search for alternatives to the Big Bang is also motivated by aesthetic and philosophical considerations. Many physicists feel uncomfortable with the idea of an absolute beginning, a moment before which nothing existed, not space, not time, not matter, not even the laws of physics. This seems to place the ultimate origin of the universe beyond the reach of scientific inquiry, relegating it to the realm of metaphysics or theology. An eternal universe, whether cyclical or evolving through some other process, avoids this problem by eliminating the need for an absolute first moment. There's always something before, always a prior state that can potentially be studied and understood. However, eternal universes come with their own philosophical baggage. If the universe has existed forever, why does it appear to have a finite age? The cosmic microwave background, the abundance of light elements, and the expansion of space all point to a universe that was very different 13.8 billion years ago. Any eternal universe model must explain these observations while avoiding the conclusion that there was an absolute beginning. This typically requires proposing specific mechanisms or phases that reset the universe's clock, making it appear young even if the underlying reality is ancient or timeless. One particularly intriguing idea is that our universe might be a simulation running in a more fundamental reality. This possibility, while it sounds like the premise of a science fiction film, is taken seriously by some physicists and philosophers. If consciousness and physical reality can emerge from computational processes, then it's at least conceivable that our entire universe is a sophisticated simulation created by intelligences in another realm. In this scenario, the Big Bang would simply be the initialization of the simulation, the moment when the program started running. What we interpret as fundamental laws of physics would be the rules programmed into the simulation. The simulation hypothesis is extraordinarily difficult to test, which makes it controversial. Some have suggested looking for glitches or computational artifacts in the fabric of reality, but it's not clear what such evidence would look like or whether a sufficiently advanced simulation would produce detectable anomalies. Moreover, the simulation hypothesis doesn't really solve the problem of origins, it just pushes it back one level. We still need to explain where the simulators came from and what kind of universe they inhabit. Nevertheless, the hypothesis serves as a reminder that our assumptions about reality might be far off the mark, and that the universe's true nature could be stranger than anything we've yet imagined. Returning to more testable alternatives, some cosmologists have explored models where the Big Bang was preceded by a contracting phase. In these cyclic or ekpyrotic scenarios, the universe expands for billions of years, eventually stops expanding and begins to contract, collapses to a very small size, and then bounces back into a new expansion phase. Each cycle might last trillions of years, with our current expansion phase being just the latest in an infinite series. The Big Bang we observe would be a bounce point between cycles rather than a true beginning. These models face significant challenges. During the contracting phase, tiny irregularities in the distribution of matter and energy would grow, potentially creating catastrophic inhomogeneities that would prevent a smooth bounce. The universe might fragment into disconnected regions or form black holes that would disrupt the cyclic pattern. To make cyclic models work, physicists must invoke special mechanisms that smooth out these irregularities before each bounce. Whether such mechanisms can be realized in a realistic theory remains an open question. Another class of alternatives involves modifying our understanding of time itself. What if time didn't begin at the Big Bang, but rather emerged from a timeless quantum state? Stephen Hawking and James Hartle proposed a model where the universe has no boundary in time, no definitive starting point. In their approach, as you go back toward the Big Bang, time gradually becomes more space-like, blending smoothly into space in a way that eliminates the singularity. The question, what happened before the Big Bang? becomes meaningless. Not because there was nothing before it, but because the concept of before doesn't apply. It's like asking what's south of the South Pole. The question itself is based on a category error. The no-boundary proposal is mathematically elegant and avoids the conceptual problems associated with an absolute beginning. However, it relies on controversial assumptions about how to apply quantum mechanics to the entire universe. Quantum mechanics was developed to describe small systems like atoms and particles, not cosmic wholes. Extending it to the universe as a whole requires making interpretive choices that physicists don't universally agree on. Different choices lead to different conclusions about what the universe's quantum state would be and whether a boundary in time exists. String theory, mentioned earlier as a candidate for quantum gravity, has generated numerous alternative scenarios for the universe's origin. In some string theory models, our universe exists on a three-dimensional membrane, or brane, floating in a higher dimensional space called the bulk. The Big Bang could have been caused by our brane colliding with another brane. This collision would have released enormous energy, heating our brane to extremely high temperatures and initiating the expansion we observe. Before the collision, both branes might have existed for an indefinite period, meaning the Big Bang marks the beginning of our universe's current phase, but not the beginning of reality itself. Brane cosmology offers rich possibilities for explaining various cosmological puzzles. The weakness of gravity compared to other fundamental forces might be explained if gravity can leak into extra dimensions while other forces are confined to our brane. The uniformity of the cosmic microwave background might result from processes occurring in the higher dimensional bulk before the brane collision. However, these models also make predictions that should be testable. They predict specific patterns in gravitational waves and particular signatures in the cosmic microwave background that differ from standard Big Bang predictions. Future observations might be able to confirm or rule out these scenarios. Yet another alternative comes from considerations of quantum cosmology. In quantum mechanics, particles can tunnel through barriers that classical physics says should be impenetrable. This tunneling process allows for the possibility of the universe itself tunneling into existence from nothing. Alexander Vilenkin proposed that the universe could have emerged from a quantum fluctuation, spontaneously tunneling from a state of nothingness into a small, inflating universe. In this picture, the Big Bang wasn't caused by anything, it simply happened as a quantum event with a certain probability. This idea raises fascinating philosophical questions about the meaning of nothing. When physicists say the universe came from nothing, they don't mean absolute nothingness in the philosophical sense. They typically mean a quantum vacuum, a state governed by the laws of quantum mechanics where particle-antiparticle pairs constantly pop into and out of existence. But quantum mechanics itself is something, a framework of laws and mathematical structures. This means the quantum tunneling hypothesis doesn't truly explain how everything came from nothing. It explains how a universe could emerge from a quantum vacuum governed by pre-existing physical laws. The question then becomes, where did those laws come from? Some physicists argue that the laws of physics might be the only things that can exist necessarily without requiring further explanation. Mathematical structures and logical relationships, they suggest, have a kind of existence, independent of physical reality. The universe, in this view, is simply the physical instantiation of certain mathematical structures. The laws don't need to be created or caused, they just are, and the universe exists because these mathematical structures have the property of self-consistency and generative power. This is a deeply philosophical position that blurs the boundaries between physics, mathematics, and metaphysics. Others take a different approach, suggesting that the laws of physics themselves might have emerged or evolved. In the earliest moments of the universe, or in the timeless quantum realm before the Big Bang, perhaps no fixed laws existed. Instead, the laws we observe might have crystallized out of a more primordial chaos, selected from a vast space of possibilities by some process analogous to natural selection. This idea is highly speculative, but it offers a potential explanation for why the laws take the particular form they do. They're not arbitrary divine decrees or brute facts, they're outcomes of a cosmic evolutionary process. The role of consciousness in cosmology presents yet another fascinating angle. Some interpretations of quantum mechanics suggest that observation plays a fundamental role in determining physical reality. In the famous double-slit experiment, quantum particles behave differently when observed than when unobserved, as if the act of measurement affects the outcome. Extending this idea to cosmology leads to strange possibilities. Did the early universe exist in a superposition of different states until conscious observers emerged to collapse those possibilities into a definite reality? If so, the existence of consciousness might be intimately connected to the nature of cosmic origins in ways we don't yet understand. These ideas verge on the wildly speculative, and most physicists would caution against taking them too literally. Yet they illustrate how deeply puzzling questions about the universe's beginning remain. We're not just missing a few technical details that future experiments will fill in. We're grappling with conceptual problems that challenge our basic assumptions about existence, causality, and the nature of physical law. The universe's origin touches on questions that have occupied philosophers for millennia, and it's not clear that science alone can provide complete answers. Nevertheless, science continues to make progress. The observational tools at our disposal are more powerful than ever. Space telescopes like the James Webb Space Telescope are peering back to the earliest galaxies, formed just a few 100 million years after the Big Bang. These observations are testing our models of how structure formed in the early universe and whether those models are consistent with what the Big Bang theory predicts. Particle accelerators, while unable to recreate the conditions of the Big Bang itself, can simulate aspects of the early universe's physics, probing the behavior of matter and energy at extreme temperatures and densities. Gravitational wave detectors are becoming increasingly sensitive, opening the possibility of detecting primordial gravitational waves from the universe's first moments. If inflation occurred, it should have generated a particular pattern of gravitational waves that would leave an imprint on the cosmic microwave background. Detecting this signal would provide strong evidence for inflation and constrain what happened in the universe's earliest instance. Conversely, failing to detect these waves after exhaustive searches might suggest that inflation didn't occur, forcing cosmologists to reconsider the standard picture. Advances in theoretical physics are equally important. New mathematical techniques are allowing physicists to explore quantum gravity in ways that weren't possible before. Computer simulations of the early universe are becoming more sophisticated, incorporating quantum effects and testing whether particular scenarios can produce the universe we observe. These simulations can't prove what actually happened at the Big Bang, but they can rule out scenarios that are inconsistent with observations and identify which models are worth pursuing with more detailed study. The interplay between theory and observation is what makes cosmology a genuine science rather than pure speculation. Theoretical physicists can dream up countless alternatives to the Big Bang, but only those that make testable predictions and survive confrontation with data can be taken seriously. This is both a strength and a limitation. It ensures that cosmology remains grounded in empirical reality, but it also means that some questions might remain forever beyond our reach if they concern aspects of reality that leave no observable traces. For instance, if the universe truly is cyclic, what happened in previous cycles might be completely inaccessible to us. Each bounce might erase all information about prior states, resetting the cosmic clock and leaving us with no way to reconstruct the past beyond a certain point. Similarly, if our universe is one of many in a multiverse, we might never be able to observe the others directly, limiting our ability to test the multiverse hypothesis. These scenarios might be true, but if they make no observable predictions different from simpler alternatives, science might be unable to confirm them. This raises an important question about the goals of cosmology. Is the aim to find the true account of cosmic origins, whatever that might be, or is it to find the simplest model that explains all observations? These goals might diverge if the true explanation involves unobservable elements. Some physicists prioritize empirical adequacy, arguing that science should focus exclusively on explaining what we can observe and measure. Others contend that truth matters even when it's not directly testable, and that we should follow theoretical reasoning wherever it leads, even into realms beyond observation. These methodological debates reflect deeper disagreements about the nature of scientific knowledge. Is science discovering an objective reality that exists independent of human observation, or is it constructing models that help us predict and control our experiences? Most physicists adopt a pragmatic middle ground, treating their theories as approximately true descriptions of reality, while remaining open to the possibility that future discoveries might require radical revisions. This attitude has served science well, allowing for revolutionary changes in understanding when new evidence demands them, while maintaining continuity with past successes. The history of cosmology itself provides valuable lessons. There was a time when nearly all astronomers believed the universe was static and eternal, with stars and galaxies distributed more or less uniformly through infinite space. Einstein himself initially modified his equations to ensure a static universe, adding a cosmological constant to counterbalance gravitational collapse. The discovery that the universe is expanding demolished this picture, forcing a complete rethinking of cosmic origins and evolution. What seemed like settled knowledge turned out to be profoundly wrong. Could we be making a similar mistake today? Is it possible that future discoveries will overturn the Big Bang Theory as completely as the expanding universe overturned the static model? Absolutely. Science is always provisional, always subject to revision in light of new evidence. The difference is that the Big Bang Theory has survived far more stringent tests than the static universe ever did. It has made numerous successful predictions, and no alternative has yet matched its explanatory power, while also solving the problems it faces. But this doesn't mean it's the final word. What would it take to definitively prove that the universe didn't begin with the Big Bang? We would need compelling evidence that contradicts the theory's core predictions or supports a specific alternative. This might come from unexpected patterns in the cosmic microwave background that can't be explained by standard Big Bang cosmology. It might come from observations of objects that appear older than the universe is supposed to be, suggesting the Big Bang wasn't really the beginning. It might come from successful predictions of an alternative theory that the Big Bang can't accommodate. Any of these developments would force a major reassessment of our cosmic origin story. Interestingly, some recent observations have raised eyebrows. The James Webb Space Telescope has discovered galaxies that appear to be more massive and mature than expected for their early formation time. According to standard Big Bang cosmology, there should not have been enough time for such large, well-developed galaxies to form so soon after the universe's beginning. While these observations don't yet constitute a crisis for the Big Bang Theory, they might be explained by refining our models of galaxy formation. They serve as a reminder that the universe can still surprise us. The discovery of anomalies in the cosmic microwave background has also sparked debate. The radiation is remarkably uniform, but there are subtle patterns in its temperature fluctuations that some researchers claim are difficult to explain within standard cosmology. These patterns include unexpected alignments and asymmetries that might hint at new physics, or at least at aspects of the early universe we haven't fully understood. Again, these observations are controversial and might ultimately be explained within the conventional framework, but they keep alive the possibility that something important is missing from our current picture. Dark energy, the mysterious force causing the universe's expansion to accelerate, remains one of the biggest puzzles in cosmology. We don't know what it is, why it exists, or why it has the particular strength it does. Some cosmologists wonder whether dark energy is connected to the conditions at the universe's beginning. Perhaps the same field that drove inflation continues to exist today as dark energy, influencing the universe's expansion billions of years after the Big Bang. Or perhaps dark energy is evidence that Einstein's theory of gravity needs to be modified, which could have implications for what we think happened at the universe's origin. The nature of time itself might hold keys to understanding cosmic origins. Our everyday experience treats time as absolute, flowing uniformly from past to future. Einstein's relativity showed this isn't quite right. Time can stretch and compress depending on velocity and gravitational fields. Quantum mechanics suggests time might be even stranger at the smallest scales. Some theories propose that time is quantized, coming in discrete chunks rather than flowing continuously. Others suggest time might be an emergent phenomenon, not fundamental to reality but arising from deeper structures. If time is emergent, questions about the universe's beginning take on new meaning. Instead of asking what happened at the first moment of time, we might ask how time itself crystallized out of a timeless quantum state. The Big Bang would mark not the beginning of time, but the transition from a timeless realm to a temporal one. This is conceptually challenging, but might resolve some of the paradoxes associated with cosmic origins. Without time, there's no need to explain what came before or what caused the first moment. Causality itself only becomes meaningful once time emerges. These radical ideas push physics to its limits and beyond. They require us to abandon cherished assumptions and embrace possibilities that seem bizarre by everyday standards. Yet this is precisely what physics has always done. Quantum mechanics revealed that particles can exist in multiple states simultaneously. Relativity showed that space and time are flexible and intertwined. Who's to say that our current understanding of cosmic origins won't seem equally naive 100 years from now? The question of whether the universe began with the Big Bang is ultimately a question about the limits of human knowledge. Can we use observation, experiment, and mathematical reasoning to reconstruct events that occurred billions of years ago under conditions we can never directly reproduce? History suggests the answer is yes, at least to some extent. Cosmologists have successfully predicted phenomena like the cosmic microwave background and the abundance of light elements based on their models of the early universe. These successes give us confidence that we're on the right track. But history also teaches humility. Every generation of scientists has been convinced they were close to a complete understanding of nature, only to be proven wrong by the next generation's discoveries. The universe is under no obligation to make sense to human minds or to operate according to principles we find intuitive. Our brains evolved to help our ancestors survive on the African savanna, not to comprehend quantum gravity or cosmic origins. The fact that we can understand anything about the universe's beginning is remarkable and perhaps surprising. So where does this leave us? The Big Bang theory remains the best scientific explanation we have for the origin and evolution of the universe. It's supported by multiple lines of evidence and has survived decades of testing. But it's not complete. It leaves fundamental questions unanswered and contains conceptual problems that suggest our understanding is incomplete. Alternative theories exist, some of which avoid certain problems with the Big Bang while introducing new challenges of their own. The possibility that the universe didn't begin with the Big Bang is more than idle speculation. It's a serious scientific question being actively investigated by cosmologists around the world. Whether the universe bounced from a prior contracting phase, emerged from a quantum fluctuation, resulted from colliding higher dimensional objects, or originated in some way we haven't yet conceived, remains uncertain. What's clear is that the story of cosmic origins is far from closed. Each new observation, each theoretical advance brings us closer to understanding where we came from and how everything began. Perhaps the most profound realization is that the question itself, did the universe begin with the Big Bang or not, might be too simplistic. Reality might be stranger and more nuanced than any binary choice suggests. The universe's origin might involve aspects of multiple theoretical frameworks, each capturing part of the truth. Or the very concepts we're using, beginning, cause, time, existence, might need to be radically reimagined before we can properly frame the question, let alone answer it. What's certain is that humanity's quest to understand cosmic origins will continue. We're driven by an insatiable curiosity about where we come from and how we fit into the larger cosmic picture. Every generation adds its contribution to this grand endeavor, building on the achievements of the past while pushing into unknown territory. The scientists of the 21st century are writing a new chapter in this ancient story, using tools and insights unavailable to their predecessors. Future discoveries might vindicate the Big Bang Theory, filling in the remaining gaps and answering the outstanding questions within its framework. Or they might overturn it, revealing that the universe's true origin story is radically different from what we currently believe. Either outcome would represent a triumph of human intellect and curiosity. Either way, we'll have learned something profound about the nature of reality and our place within it. The universe doesn't care whether we understand it. The cosmos existed for billions of years before humans evolved to contemplate it, and will continue long after we're gone. But we care. We want to know. This desire to comprehend the incomprehensible, to explain the seemingly inexplicable, defines us as a species. It's what drives us to build ever larger telescopes, design ever more sophisticated experiments, and develop ever deeper theories. In the end, the question of whether the universe began with the Big Bang is part of a larger inquiry into the nature of existence itself. Why is there something rather than nothing? Why does the universe have the properties it does? Is our existence a cosmic accident or the inevitable outcome of deep principles we've yet to discover? These questions transcend science, touching on philosophy, theology, and the deepest human concerns about meaning and purpose. Science may never provide final answers to these ultimate questions, but it can illuminate them in ways that pure philosophy or theology cannot. By studying the universe with rigor and precision, by testing our ideas against the hard facts of observation, we constrain the space of possible answers and eliminate explanations that don't match reality. We may never know everything, but we can know more today than yesterday and more tomorrow than today. The journey of discovery continues. Each generation of cosmologists stands on the shoulders of those who came before, seeing a little further into the cosmic past and understanding a little more about how everything came to be. Whether the universe began with the Big Bang or emerged through some other process, the story of how we came to ask these questions and develop the tools to investigate them is itself a remarkable achievement. We are, in a very real sense, the universe awakening to contemplate its own origins. And so we press forward, armed with mathematics and observation, imagination and skepticism, forever seeking to understand the greatest mystery of all. How did all of this begin? The answer, when we finally find it, will be worth the wait.